So let's get started. We sort of, before we started here, people introduced themselves, but Tarcisio didn't really get a chance yet. So this is your chance now, the beginning of the talk. So I will leave the stage to you, and thank you very much for coming to talk to us.
Thanks, Ayal, for the invitation. Hello, everyone. I hope you guys are doing well. My name is Tarcisio. I am a technical account manager at RedHat, and today's topic is AutoML. Uh, what we'll discuss today. I always like to start by talking a little bit about artificial intelligence and machine learning, some concepts, some examples, and some numbers. Then we'll talk about machine learning workflow, the main and common stages when you work with machine learning development. Then we will talk about AutoML and again some concepts, how it works, the main algorithms behind, and frameworks to implement. And at the end, a demonstration of how to get started with AutoML. Okay, we can define artificial intelligence as the science and engineering of creating intelligent machines, especially intelligent computer programs. And one of the ways to create these intelligent programs is through machine learning. So machine learning is a set of algorithms that are used to allow a computer to identify patterns in past data and use those patterns to predict future results. Computer vision and natural language processing, for example, both make heavy use of machine learning. And why is it important? Intelligent applications are powered by artificial intelligence and machine learning. It can help you to accelerate business critical initiatives. Many organizations, banks, and fintechs, and many organizations are using AI and ML in production with intelligent applications that automatically discover, learn, and offer predictions and recommendations and to gain a competitive advantage and optimize resource usage. Here we have some numbers. AI has the potential to deliver additional global economic activity of around $13 trillion by 2030. 51% of enterprises indicate that their current AI infrastructure will not be able to meet future demands. And 69% of enterprises use a mix of open source and cloud-based software to power AI initiatives. We were talking before about some of those platforms like IBM Discovery and Google Cloud AI platform, for example. Here are some examples of areas where AI can be applied. Of course, we are not limited to just those, but for example, automated customer support, shopping experience, healthcare, finances, travel, navigation, and security, and many others. When we talk about machine learning, we are probably talking about neural networks. We can say that neural networks is the core of machine learning. They have this name because they are inspired by the human brain, and there are several types: artificial neural networks, convolutional neural networks, recurrent neural networks, and they can perform a lot of tasks. such as natural language processing and image classification. In the image, we can see the representation of a neural network performing the classification of images of cats and dogs, for example. And for this kind of task, probably the convolutional neural network performs better, for example. Okay, and when we talk about machine learning development, we are essentially talking about model development. A model is the implementation of your machine learning algorithm. The implementation of your convolutional neural network trained on a sufficient amount of data. For the image classification task, for example, it's a file containing all the parameters, layers of your algorithm that you can send to production to make your predictions or recommendations or any other task. But it's not just developing the model. There are actually several stages in the development life cycle of your model, in the development of your software. There is usually a workflow that needs to be followed. Here we have the main and common stage to be implemented and often automated in a machine learning workflow. Gather and prepare data to make sure the input data is complete and of high quality. This is where you make use of data storage, data lakes, message brokers like Kafka, for example. Then you have to develop the model, which includes tasks such as training, testing, and selecting the best algorithm with better performance, with better accuracy. And then you have to deploy the model in an application, and usually in different environments, such as staging environment, production environment, and making use of continuous integration, continuous deployment tools. And do the monitoring and management of that model to measure business performance, creating alerts. For example, if you are working with anomaly detection, it might be important to create an alert when an anomaly occurs, for example. And here are some tools to help you implement a machine learning workflow. Apache Spark for large data processing, for example. Airflow for creating data pipelines. Kubeflow. I really like Kubeflow, which is a platform to run experiments and create machine learning pipelines. Python, R, and Julia as programming language, and Java, right? TensorFlow and PyTorch and Keras as libraries for developing your models. Jupyter Notebooks has a development environment, and you can use public cloud platforms that have multiple services to implement your machine learning workflow, such as Google Cloud AI Platform, Amazon SageMaker, Red Hat OpenShift Data Science, for example, IBM Watson, Azure Machine Learning, and so on. Now here are 5 considerations for your AI ML platform. Build a data strategy, how you will store, prepare, and secure your data. Provide self-service access to tools. It's not cool to force the use of a tool or a technology, and provisioning these tools must also be fast, auditable, and secure, and self-servicing. Create a collaborative environment. You have data science, machine learning engineers, software developers, the infrastructure team, everyone must work, for example, using a DevOps methodology, or better yet, an MLOps methodology. Use a hybrid cloud approach. You can develop in a cloud environment for better agility, then you deploy on-premise for better data security, and run your models at the edge to improve latency. If you never heard of hybrid cloud or edge computing, I invite you to get to know them. And whenever possible, choose open source solutions, and also make your contributions to the community. Everyone wins. Oops. Okay, and one of the ways that you can implement all stages of your machine learning workflow is by using a project called Open Data Hub. With Open Data Hub, you can easily instantiate many other systems, such as Apache Spark, Jupyter Hub, Kubeflow, Seldon for model deployment, and the others. All projects are open source, and it's very easy to instantiate them. Okay, finally, AutoML. Sorry for the big intro. Automated machine learning. Automated machine learning is the process of automating the tasks of applying machine learning to real-world problems. It's the process of automating all or almost all the tasks required for your machine learning workflow. AutoML provides methods and process to make machine learning more accessible because it's easy to use, improve the efficiency of machine learning systems. That's because models and parameters are selected automatically and efficiently, and accelerate research and AI application development. That's also because a lot of tasks are done automatically. And what tasks can we automate? Pre-process and clean the data, select and construct appropriate features, select an appropriate model family, optimize model hyperparameters, design the topology of neural networks, post-process machine learning models, and analyze the results. Every task here can be automated in an automated way. Okay, here you have a comparison of a complete machine learning workflow with a simplified process using AutoML. Of course, it depends on the complexity of your workflow, but it's possible to replace almost all stages of your machine learning pipeline, of your machine learning workflow with AutoML. Detailing the stages a bit, we have data preparation, column type detection. This column is a string, this column is a number, this column is a decimal number, this column is a category. Column intent detection. This column is a feature, this column is also a feature, this column is a label, for example. Task detection. Is this a regression problem or a classification problem, or do I have to use some clustering algorithm? Okay, then you go to feature engineering, feature selection, feature extraction, pre-processing the raw data into features that can be used to train the model. And then you have model. You have to select, create, and train the model. And at the end, you have to choose the right metrics to make a correct analysis of the model's performance. Okay, and how does AutoML automate this stage? Basically, running two techniques, architecture selection and hyperparameter optimization. Architecture selection is a set of techniques for automating the discovery of the best performing statistical model for a given problem. And to find the best architecture, the best design topology, it uses algorithms such as neural architecture research or NAS and differentiable architecture research or DART. Hyperparameter optimization is also a set of techniques to find the best configurations, the best hyperparameters for your learning algorithm. Grid search and random search are probably the most widely used because they are so easy to implement. But when the search space gets bigger, when you have a lot of possible values for your hyperparameters, grid search and random search can take a long time to compute. So you can use some meta-heuristic techniques such as evolutionary optimization and Bayesian optimization, for example. Of course, there are other techniques you use for hyperparameter optimization and architecture selection. And meta-learning aims to improve learning across different tasks or data sets instead of specializing on a single one. So the efficiency of architecture selection and hyperparameter optimization can be improved by meta-learning to transfer knowledge between the tasks. Meta-learning uses meta features, metadata, or create meta models based on performance and uses them to improve efficiency. Okay, but how does Dart work to find the best architecture topology? Dart first assumes the space of candidate architectures, as we can see in the image letter B. It then places mixtures of the different operations on each edge and optimizes them by mixes the probability of each, and the network weights are optimizing by solving a gradient descendant based problem. And it gives you the final architecture from a mixture of those probabilities, as you can see in the image letter D. It looks like complex, but it's not. But the algorithm is very this algorithm is very efficient to find the best neural network architecture. For hyperparameter optimization, grid search and random search, they both work in a similar way. You have a space of possible parameters. Then the algorithm chooses a combination of those parameters and stick with those that presents a better performance. Grid search in a linear way. So, for example, for the parameter 1, goes from 0 to 10 in a step of 2, for example. So 0, 2, 4, and so on. And for the parameter 2, it goes from 0 to 1 in a step of 0.1, for example. So 0.1, 0.2, 0.3, combine them and check the performance. Random search does the same, but in a random way. So, for example, for the parameter 1, picks number 4. And for the parameter 2, 0.5, combine them and check the performance. Grid search and random search works. They work great for models with just a few hyperparameters. But for a large number of hyperparameters, you can use, for example, evolutionary optimization and Bayesian optimization. Of course, there are other techniques, but Bayesian optimization, for example, works really nice. Evolutionary optimization is inspired by biological evolution. You have a population of candidates, then we have an objective function. It's called fitness function, and with each step of generation, you select the best individuals of that population, the best individuals or best results, make some reproductions or mutations, and recheck the fitness function. If it's not good enough, if your fitness function is not good, then you go one step further, you make a new generation. Bayesian optimization has an objective function as well, which is the blue, and several optimizations are applied to form a still unknown structure, which is the black. I won't go into the math details because they are complex, but they are very easy to get started and to implement. Meta learning. Meta learning uses components such as meta knowledge, meta features, meta learning, and makes a series of assumptions based on your data to improve the efficiency of the learning algorithm, improve the efficiency of your architecture selection and of your hyperparameter optimization. Okay, here we have some frameworks that can be used to implement AutoML for a full pipeline solution. Feature engineering, model construction, and hyperparameter optimization. You can use, for example, AutoScaler to do every of those steps. I believe, okay. MLBox, for example, can be used for data cleaning, for model selection, and hyperparameter selection. The same for AutoScaler. Teapot can be used to automate your entire data science pipeline. At the end, in the demo, we are going to use Teapot. And public cloud platforms such as Google Cloud AutoML to train and deploy your models, and also to deploy your model in the Google Cloud has an application. Of course, AutoML, it is good, but it's not a silver bullet. AutoML is not good, for example, for unsupervised learning and reinforcement learning, because you don't have labels, and those are algorithms that require a deep understanding of the data and its relevance to the business. You need a business analyst at your side to get at the better insights of your data, and that's a task that AutoML it's not good to do. Also, very complex data types may also need pre-processing before starting the AutoML process to get good results. So if you have data that is very complex and you get a very poor result, a very bad result at the end of your AutoML, maybe you have to do some pre-processing in a manual way to get better results using AutoML. I do have a demo I'm going to share in a minute. Okay. You still see my screen, right? Here I have a brand new OpenShift cluster, and I have installed the operator of Open Data Hub here. And from the operator, I have instantiate a Jupyter Lab software. And I have two demos here. And I know that will look like very disappointed because this is the entire code to implement your AutoML algorithm, your AutoML task. I have here a teapot classifier. It is going to use evolutionary algorithms. So here I am specifying how many generations I want to have in the cycle. The population size, so it's going to take 15 individuals each time. The verbosity, and I want to shuffle the data. I'm going to use the ARIES dataset. I believe everyone know about this data set. It's widely used in Kaggle and in getting started in algorithms. So okay, so let me run let me create this classifier and fit it on the data. It's going to take some time because I do have 5 generations here, but I can see the progress here. Okay. Meanwhile, let's check this other demo. Here we're going to have a regression model. So it's going to do a regression model. I'm using here AutoScaLearn. This model is already trained. Let's see the leaderboard. It took 5 minutes to train in diabetes data set. Let's check the leaderboard. Here we have the rank of the algorithm with better performance to the most poor performance. So SGD works better. SGD stochastic gradient descent and Gaussian and gradient boosted the poor performance. Let's print. Here is the architecture of the model created. We can see every information of the model, and let's check the R2 score on the training dataset and test dataset. Let me check here. Okay, it is still fitting. They are running with just 2 gigabytes of memory. That's why it's slow. And I'm running both processes at the same time. Here you can see the score of each generation. It is going to print for every 5 generation, and well, At the first generation, we get a score of 97%, which is very good. And I didn't have to specify which model I'm going to use. Neither I have to specify the parameters like a running rate, the number of layers, the number of nodes in each layer. That's not necessary. I don't know why it's very slow. Okay, here we have this R2 score, and let's plot the regression model. So I have implemented this model with just 2 lines of code. Extremely easy and getting a good result for a regression problem. Here is for okay, now it's faster. And for a classifier using Tpot, it's in the generation 2. Also with 97% of accuracy, current best interval, cross-validation score. Generation 3. Okay, here is how your traditional way to create a model. So you have to use TensorFlow and Keras here. You have to specify the architecture, which is a sequential. I'm choosing a rescaling layer to rescale my image. I have to do some data augmentation to get more features. I choose another model for transfer learning. And here I'm specifying another layers like dropout to avoid overfitting of my model. I have to choose the activation function. As you can see, none of this task is necessary when you are working with AutoML. Okay, so here we have using Tpot classifier. At the end, it prints the architecture chosen, which is a random forest classifier with a polynomial features and all other information about parameters and everything. And let's see, the score was at 5 generation, was slightly better than the 30. Let's check the score. Okay, 97% of accuracy, which is really nice to get started with. So that's all the demo that I have. AutoML, as you can see, it's a very good tool to get started with machine learning, but this tool does not replace your knowledge about machine learning algorithms. It's just a tool that you can use to get started pretty fast. And
Manny has a lot of relevant links. Let me invite Manny to the stage if you don't mind. I think Manny knows the person who wrote PyCaret. Is that true?
Oh, nice.
Let's see. And he is a co-organizer of this group. So I'm inviting you to stage. Okay.
Hello,
and,
thank
Leonardo
you.
is raising his hand. Do you want to join us as well? Okay, let me bring up Leonardo because it looks like he is, I think, maybe asking to join us.
Leonardo has a question, he says.
Okay. So
maybe
join
you can speak it out or ask the question. Okay, or bring him on board. Leonardo is here. Hello, good to see you.
Hello all. Actually, I first of all, thanks for the presentation, Tarcisio. it's always good to know more about, and AutoML is an interesting and really breakthrough topic that's going on. I actually, my question is not too related to AutoML, but I like the way that you instantiate a new Python lab or Jupyter lab. How did you do that? You passed through too fast, so I didn't know. So you opened the RedHat, and I click in two buttons. Suddenly, you opened the Jupyter lab. I just want to know what kind of technology did you use to quickly instantiate your Jupyter lab instance, and if it is possible to configure. For example, I used SageMaker on AWS to run some code, but they have some limitations. I cannot put, for example, more hand memory or configure the HE, the hard disk. So can I do this kind of configuration RedHat? If you can briefly explain a little bit about, I'm really interested. Thank you.
Yes. Nice question. Thanks, Leonardo. Open Data Hub is a project. It has some engineers from Red Hat working on it, but it's a project that it's called a meta project. It's a project to instantiate another project. So in a very easy way, using Kubernetes resources, Kubernetes custom resource definitions, those YAML files, with just a few lines of code, you can instantiate another project like Apache Spark. I believe it's almost 20 projects that you can instantiate in an extremely easy way using Open Data Hub operator, and has an operator, and you can run it in any Kubernetes platform. You can run it on OpenShift platform, on Elastic Kubernetes Search, AWS AKS. You can run it on Google Kubernetes Engine. So first you install this operator, which is very easy to install on the operator. You just run a YAML file, and with this operator you choose, okay, I want to deploy Grafana, Prometheus, and Jupyter. Grafana and Prometheus for monitoring, and the Jupyter Hub or Jupyter Lab with just a few lines of code. You can also deploy Kubeflow. Usually, that's the way that I deploy a new Kubeflow using the Open Data Hub operator, because installing manually, it takes some some work to do, but using this operator, it's extremely easy to instantiate a new Kubeflow instance. OpenDataHub.io is the website, and how you can install the operator and instantiate those other projects are all there, and you can check on OpenDataHub.io. And that's how. And about AutoML, what's your second question? How?
No, it's just that. I'm more interesting if we can configure different setups. For example, increase the hard disk, or change the run, or put some GPU or TPU or whatever there.
Yes. You can do all kinds of configurations. For example, when you have a Jupyter Hub, you can, when you first run it, you choose the size of your notebook server. So I want a notebook server of a large, medium, or large, or small, and then you can create your own flavor of configuration that use your CPU and memory. And I want to use GPU, for example. If you have all kinds of configuration you can put. I am using a small machine here. That's because I only have 2 gigabits of RAM, but you can create as your own flavor.
Amazing. Thank you so much.
I think Leonardo also wanted to see how you instantiated the Jupyter notebook from the previous step where you had your system running. So is that something you can quickly show us, or is that part of the
Yes,
flow?
I can
Yeah,
quickly
I
show
think
you
that's
now.
what he also wanted to know, because my question also with this is, whilst you're showing this, is you're running this on your local machine, right? Or you're running this on a server, on a
No,
remote?
I'm running on a server on AWS. I
Okay,
just don't have enough memory.
right. Okay, that's what. Okay, that's now I understand.
Here's
So
the
you're
problem.
running it on a smaller instance as opposed to you could have run it on a bigger instance.
Yes, yes.
Okay.
Then you go in Operator Hub and search for your Open Data Hub operator. Here, then you click. Here is a warning that this is an operator developed by the community, and you click Install. After install, here is all the projects that you can instantiate from this operator. Jupyter Hub, Trino, Elira notebook. If you know Elira, it's a very good visual where you can create a pipeline from the Jupyter. You can create a visual pipeline, which is very good. Prometheus and Grafana for monitoring. Seldom for model deployment. You can deploy your model in a way that model as a service. So using Seldom, you can just select your model and it's going to be served as a microservice, which is very nice using Seldom. Argo for a continuous deployment implementation. Okay, and with the operator installed, then we installed operators. You select the operator and create instance. And let's check the YAML file. This is the default YAML file, and the default YAML file to the deploy project, he's going to deploy every project that's listed here. For example, a Kafka, it's going to deploy a Grafana, it's going to deploy a Prometheus. Oh no, but I just want the Jupyter. Here is the Jupyter. Then, no, I don't want Apache Flow. I don't want an iFlow coaster. I don't want Argo. No, I don't want the dashboard. It's very ugly. Jupyter, yes. S3, no. And here you can choose all the projects to deploy. I made the full installation, and then he instantiates a lot of things. Let's check the pod. I have an iFlow running. I have an Argo server. I have a Jupyter Hub running. So with just those few clicks, you can create all those projects in a very easy way. I really like the Open Data Hub project. And as I told before, you can implement an entire machine learning workflow just from the projects that you can instantiate from this operator. For example, if you want to store your images on Next3 implementation, you can use Ceph and storage implementation. You can instantiate a PySpark, a Jupyter with an image that already contains TensorFlow, for example. You can instantiate Kubeflow. I really like Kubeflow. And you can deploy your model using Seldon or OpenShift and get a metrics using Grafana or Prometheus and store those metrics on Ceph, for example. That's it.
Really awesome. Thanks.
Have you tried deploying all of this on a local machine, and what's like the minimum configuration you think one would need to do that? Because I mean, if you do it on an Amazon instance, even that 2 gigabytes is going to be expensive, right? I'd rather run it on a local machine, and you can put lots of gigabytes and disk space and processors, and it won't cost you so much as on an Amazon machine on a long period of time. So what's your experience being, and what kind of a configuration you would recommend? Because I'm someone who likes to experiment things locally before I deploy it onto the server, because cloud is expensive.
Okay. Yes. Well, for OpenShift, for example, you need a local machine with 16 gigabits of memory just for running OpenShift. And well, you can choose the configuration of each project, but I believe for machine learning and to run here, just for Jupyter, I have 2 giga, which is not good. But for an entire pipeline, I believe you need at least 32 gigas of memory, 16 just for the platform, for your Kubernetes platform, just like OpenShift, and 16 for your
rest of the project.
Yes, the rest of the project.
Okay. Because it'll be great to create some sort of a Terraform installation, unless Open Data Hub is already doing that under the hood, and then play around with it on your local machine. When it works, then you can create a cloud instance and deploy it there, right, using some configuration and some deployments. Or we could deploy it on OpenShift itself. Does OpenShift allow you to do that? Can I host projects on OpenShift?
Yes.
I mean, on your cloud instance, not the local instance, the cloud instance of OpenShift. I don't know if that is a sensible question.
I don't know if I get your question, but you are trying to deploy your project in a distributed environment or something?
Yeah, so I know from my past experience that you could have an account or an instance on OpenShift.
Yes.
I don't know how much capacity you give, but can you then run projects on that cloud platform, on the cloud instance?
Oh no, that OpenShift trial gives you just one node with 80 giga.
Okay, that's very basic.
It's not nice to. Machine learning usually requires a lot of space, a lot of memory. You have to, for example, you have to load your entire data set in memory sometimes. You have to need use of cache. Many of the algorithms makes a lot of use of cache, so you need a lot of memory and. Well, what I see in some clients, my clients, they have 2 problems when they are working with machine learning. One of the problems is the compliance about the data. So they are not allowed to upload the data for the cloud, for example. They are not allowed to upload some of the data to the AWS or something. Then you need to have some very
powerful machines.
Yes, very powerful machines like IBM Z, like other very powerful machines.
Red Hat doesn't supply hardware. Does Red Hat only supplies software, isn't it?
The second problem that I see is the price. AWS, SageMaker, when it's very good to get started, but with time and when the data increase a lot, the prices
the cost
increases.
The cost of maintenance, cost of usage is very high. Yes, but hence I was asking local machine, what is the best configuration? Because I know from my past experience, people used to spend nearly $6,000 a month on AWS bills or on cloud bills, let's say, right? Let's not pick any cloud provider, on cloud bills. Then they said, you're going to take $1,700 or 1,700 pounds each and take 2 separate mega machines and really powerful machines with dual GPUs and 64 gigabytes RAM and SSD and everything. Only 1,700 pounds or so at that time. I can't remember, maybe 2,000 pounds per machine. And then their $6,000 bill just vanished, because now they don't run those loads on the cloud. They just run it on this mega 64 gigabits memory dual card, I don't know, quad core or pentacore machine, and it takes almost the same amount of time, maybe less, because on the cloud you would have to also instantiate a machine that big, and you get a big bill from that, right? So, and then they store results on the cloud, right? So the S3 bucket doesn't cost much to store results in, right? So that's what they were using the computer for.
By the way, Bob, another question. I'm sorry to interrupt. Perhaps we'll give Bob a chance also to ask.
Sure. Yeah. Sorry about that. Bob, please go ahead with your question.
Yeah, am I coming through okay?
Yes, we can hear you.
Great. I was just curious, the IRIS database, of course, is a parametric data, application or use case. What would have been different in the demo if it had been imagery of irises instead of the parametric data about irises? So what's different what has to be done differently if you're doing images as the thing that you're training against?
We are using images. The iris data set. Okay. Let me. You have to change it often, right? Because they are going to automatically choose the best algorithm for your. They are going to preprocess the data of image. They are going to transform it in a, in a matrix of values, and each point of the matrix is the color, for example. So this preprocess, you have to change in nothing the algorithm to get it started. For example, I don't know if you guys will still see my screen. Yes. For example, here I am choosing the width and the height of the image, right? It's going to rescale any image to 160 to 160 to 160. It's going to rescale the image to fit this. Every parameter here is going to do automatically if you use an AutoML tool. You don't have to choose those parameters. Your features can be images. You have to change nothing. Probably if I just change here the data set type, it's going to work exactly the same.
Just wanted to comment in general, regardless of the AutoML, what you're asking is the difference between traditional machine learning and deep learning. In traditional machine learning, we would do feature engineering, and we would try to extract features. Like in this case, it would be the size of the leaves, etc. Features of the plant that maybe experts decided that they are important for us or they are enough for us to distinguish between them. While in deep learning, you would normally just let the deep network decide what the features are. So you will give it the raw image, give it the pixels in many cases, and it will, as it goes layer by layer, it will extract features, and then very simple features, and on top of it, more complex and complex features until it figures out enough to detect what it is. So this I think was a revolution of deep learning, where it actually basically tells people, I don't really need you to tell me what the features are. I can figure them out throughout all my layers.
Yes.
And when we talk about architectural search for neural networks, part of it is how we build a network that is capable of actually getting the features out that we need for that problem without throwing too many layers and too much computation, basically power into it, because each additional layer makes the training take longer, etc., require more CPU, more energy. It sounds like you wanted to also add to that, Tarcisio.
So I believe I lost the audio.
Yeah, Tarcisio, I'm not sure if you are talking, Tarcisio. We could not hear you.
Hello, hello.
There you are.
Are you guys listening?
I can hear you.
We can hear you. Maybe you can hear us. I'll message Tarcisio.
Okay. There was an overview of AutoML. I don't know, guys, if you have more questions, or you can reach me at LinkedIn. I already have the LinkedIn of Eyal and Mani and Bob. Please feel free to reach me, and we can talk more. Thanks, Eyal, again for the invitation.
Thank you for joining us. Thank you for speaking at our virtual user group, and thanks everybody for showing up, going through the hoops of the wrong links that I sent, and some issues we had with their meet. And hopefully next meeting it will be smoother. We may try to figure out somebody to test the links before the meeting, that somebody who's not the organizer. So thank you. This will go on YouTube soon, and I will share the link once it does. And Tarcisio, if you want to share slides or anything else, best way probably is in the meetup itself, in the comments of the meetup, and people can see it there. So again, thank you very much, everybody, and see you next time.